Hello everybody. Today we're going to do the moving loads. Um, Moving loads applied to the bridge with wheels are called moving loads. In the design of the bridge, the majority of the moving loads are categorized as loads known as a couple. Okay, these loads are considered as a couple. The minimum wheels for the load to be classified as a couple, you need at least two wheels, and then it is considered as a couple. Which range from the load range from in this load range in the size from having two wheels to many wheels. When a load is classified as a couple, you don't have to put all these wheels on the bridge, but instead combine all of them into a single concentrated load, which is called as a resultant load R right here. Or in other words, you have to resolve all these loads into one. Okay. The line of action for the resultant load R lies between these three wheels, with the unknown lever arm, okay, which is an X. The X distance from the first wheel is the distance of the center of gravity of the three wheels, and is considered to be the line of action for the resultant load R right here. We need to take the sum of the moment at point R to determine the value of X. Okay, we take moment here and we can determine the value of X. When the moment is taken at point R, we need to figure out how many lever arms each wheel needs to point in the direction of R. We need all these lever arms from the loads to point R. So the first load we're gonna calculate for the lever arm for P1, the first wheel, is X. Okay, because we're taking moment here, we need the lever arm from the load to the point R. The lever arm for 10 kilonewton is X, and next is the lever arm for the 15 kilonewton right here, right? So the 15 kilonewton distance is 4 up from wheel 1 to wheel 2. So cutting that line with the line of action of the R, that would equal to that would be equal to 4 right here. This is 4, and then minus X, this one here. So the remaining distance from wheel 2, which is 15 kilonewton, is 4 minus X. Alright, and the next lever arm for the 20 kilonewton is this is 10, total length is 10, alright, and then minus that with X. So therefore the lever arm for 20 kilonewton is 10 minus X. Alright, so when you take moment point R, you have to apply the sign convention right here, the summation. Number one is the summation of moment at the axis of rotation is equal to 0. you put everything into 0 as your equation. Alright, so the summation of moment at r is equal to 0, the counterclockwise taken as negative. Okay, when you take moment at r, all these forces will rotate around the axis of rotation. When you take moment at r, that is the axis of rotation, and all these forces here, the 10, 15, and 20 kilonewton, will rotate around that point, right? So the 10 kilonewton will rotate right here. The rotation is right here, laid out here. We rotate, and that is a counterclockwise rotation. Alright, this is the point R. And the 15 kilonewton will rotate in this direction, and that is a clockwise rotation. And the 20 kilonewton will rotate in this direction, and that is also a clockwise rotation. So we have all that rotation, we have all the lever arms, and then we can start the first condition of equilibrium, which is the summation of moment at the axis of rotation. So summation of moment, taking moment at the summation of moment at point R is equal to 0. The reason why it is equal to 0 is for the condition of equilibrium. So all of the forces here are in equilibrium at that point R, right here, right? It's like you have a balance, and that point here is the distance of x from wheel 1, right? So, and the counterclockwise is positive. Alright, now when you rotate, now when you take the moment, now 10 is going in the clockwise rotation, and 15 is 10 is a counterclockwise rotation based on the moment right here, and this 15 kilonewton will rotate in a clockwise rotation as well as the 20 kilonewtons. So therefore now taking moment at r is equal to 0 for 10, and the lever arm we calculated is x plus 15 times 4 minus x right here, and then 20 times the lever arm, so 10 minus x is equal to 0, and that is your equation 1. Alright, simplifying all this, 10x plus 15 times 4, and then x times 15 equals to minus 15x, plus 20 times 10 is right here, and then 20 times minus x equals to minus x times 20 is equal to 20 minus x equal to 0. Simplify again. Now the 15 times 4 is equal to 60, and then 15x remains as 15x, and then 20 times 10 equals 200, minus 20 times x is equal to 0. Now to simplify this equation, you have to collecting like terms with an x, and then put this in this side here, all the x's is right here, and then all the whole number would be here. So 60 plus 200 minus 10x minus 15x minus 20x plus 60 plus 200 is equal to 0. That's equation 2. This equation 2 here, or equation 1, once you found the value of x, you substitute this value and see if that with the x value here that will equal to 0, then the value of x is correct. This is where you check if x is correct. You substitute that value of x to any of this equation here, and that will be 0 is equal to 0. Then the loads here, the wheel loads here is in equilibrium, and x is correct. So when you determine the value of x, okay, so continue here. Now here's the continuation. X is equal to, you factor these out, the x outside of this, so you have this 10 plus 15 plus 20 plus 60 plus 200 is equal to 0. Here factor the minus x outside of this 3 right here, and then now is x is equal to minus 60 over minus 45. Alright, so the sum of this 10, 15 plus 20 is equal to 45, so right there. And then we cross multiply this, the 45 will go under the 260, and now the mathematical operation, the law of the quotient, the law of division in mathematics, when you divide a number, when you divide the number having a like sign, the quotient is positive right here. So this is positive, and the answer is 5.7778, and then you round it off to the nearest 5.778. So when you check this to any of this equation, that would be 0 is equal to 0, but there are round offs, so don't worry about there's a very small remainder sometimes. It's because of the calculator rounds up. So pay attention to the rotation of these loads here. So when you take a moment at any point, the remaining loads will rotate around that axis of rotation. Alright, so this is now the solution of the moving loads with 3 wheels. There are several wheels, depends on the what kind of transportation is you're having to be applied to them. Now when x is found, that is now the time you apply the resultant load to the bridge, depending on the position of these 3 wheels. The position of these 3 wheels depends on the distance of the first wheel to the support of the bridge. Alright, so W1L is the distance of the first wheel to the support. So this thing moves, this moving loads moves on top of the bridge. So the location of the point R depends on how far is wheel 1 from the support, and if distance W1L is 1 meter, you add the X, and that is the point where you apply the resultant load. As I said before, in this classification of loads, you don't need to solve the shear and reactions and all that 3 wheels. You only need 1 wheel, the reaction, the resultant force applied to the bridge. I don't know if I can show you something here. Now here's the application of the resultant force. So you need that X to pinpoint the actual location of the resultant force on the bridge based on the distance of wheel 1. These wheels, these moving loads can move around, depends on the position this. So based on the position of the resultant force, you can solve the shear diagram and the moment diagram as well, the maximum moment due to this load. This is just the 2 loads. This is an example, it's the same as this one because of the resultant to be 1. This is the layout for the shear diagram, and this is for the moment diagram. The moment here is PL over 4. Alright, so we're gonna derive that later on. and see you to the next video. Bye.